Hey Aiken, how are you, my friend? I'm doing fantastic, my dude. How you been? Which is my other game. There we are. That's where I'm at, right there. Playing the new F1 game. Very good, very good. I've been playing a lot of Final Fantasy 14, so that's what I've been doing. Getting through the content again. FA Cup trial was pretty decent. Saw members only. Yeah. This is actually pretty. It's gonna be pretty decent. I won't lie. It's gonna. I'm just actually one thing I'm kind of worried about is what the fixtures around the FA Cup match is gonna be. So obviously they gotta move fixtures around and whatnot in order to accommodate that. And you're kind of hoping that the team's not too taxed or gassed by the time that comes around. So because we already have a very games may be spread out, but one thing I worry about is just like overall fitness. So uh, we have a pretty stacked preseason, so you don't want to like grind them into dust either. It'd be like a 4-day gap between FA Cups games at least. Yeah, okay. Well, if there's a 4-day gap, then that's fine. You just want to be up at 100% fitness though. So like I feel that a lot of because of COVID last year, that was kind of a one big thing between a lot of teams that they just had fixture congestion. So um, hopefully this year that won't be the case. Outside of that, I don't really have many concerns outside of that. So I don't think they've posted the fixtures yet for the league, have they? I could very well be wrong, but I don't think they posted up anything for that. I checked their website like a few days ago. Yeah, okay. All right, that's what I thought. That's what I thought. Yeah, I saw the tables. Yeah, I saw the tables are out, but I just needed to know if they're what the specific fixtures are and the dates and everything behind that. You have the FA Cup draw now. It's just a matter of now it's just a matter of just waiting, playing the waiting game. That's the goal. Actually, when is the date of that FA Cup game off the top, man? Every single season, Aiken, is a massive challenge. Every single season, but we are always up to the task. This season hopefully will be no different. I agree with the increased competition, but our guys looked really good in their preseason contest. Hopefully that carries over to the regular season. Lee Wen, hello! Hey, good to see you, Lee Wen. We missed you yesterday. I hope you're doing good. Did you have internet issues, or were you just like busy with family stuff? I was like, oh, where's Lee Wen? Like, oh my goodness, no Lee Wen. I was a little concerned, but yeah, we got a couple sections in yesterday. Your internet crashed. No, sad phase. Well, yeah, I know there's not. I know you've said your internet has been kind of really spotty. So to be fair, I'm not gonna hold that against you. I am not gonna hold that against you in the slightest. I know you come out here for the most part every class, so you know you're fine with me, Lewan. Anytime. Let's see here. Let's see. 21st of August to Chipstead. Okay. All right. 21st of August. 21st of August. Gotta remember. What, Lee Wen? You don't have to be sorry. No, not at all, Lee Wen. Nothing to be sorry about. That's something you can't control. You know. Not everywhere is going to have necessarily reliable internet. So, nothing to be sorry about whatsoever. Those things happen. And like I said, I know you make your way out every class, so I know that's not such a big deal. If you accidentally miss a day because of something you can't control. So, it is what it is. Holy smokes, Aiken! Aiken with the sub, man. Hey, thanks, dude. Thanks for the sub, my friend. Aiken, I'm gonna make it. Aiken, I'll make it up to you. I'll make up this sub to you. Thank you so much, my friend. That's super kind of you. I'll make it up to you. I know how. I know how to make it up to you. I will. I hopefully after the 19th in 5 days, right? My first payment from Twitch came through. Hey, very nice, very nice. It was like what, $100 or something like that. I know they do it like $100 a piece or something like that. I've only ever received. I only had 85. Sent it earlier. Oh, no problem, Lee Wen. Of course, I understand. Hey, Wade, how we doing? Hey, you can definitely get a thumbs up from me, man. Wade, my dude, Wade, how you been? Yeah, it was supposed to be 100. Yeah, I've gotten a couple of those $100 ones. I've only gotten 2 in the past year. You know what? I don't do it for the money anyway, so I do it for the fun. Weird flex. I'm only telling you how many I've gotten. I've only gotten 2. So it's like if you get it every so often, it's like you're doing really well. If you get it like every once in a while like I do, then it's like okay, you're doing pretty you're doing it for whatever. So there's no difference, believe me. Believe me, a couple $100 doesn't mean a whole lot to me, so it's nice to get though. So but I never thought I would get a couple of $100 to be honest from Twitch. I thought I would just be teaching classes, but hey, you know, it's I just hope you surpass. I just hope Aiken that you surpass me, my man. That's what it's about. Elizabeth, hello, happy Wednesday. Rip no founder's badge. Oh yeah, that got taken quite a while ago, my friend. You're many months a little too late. At some point, I'll see a guy called Major Mad. He'll probably come in at some point. Happy Wednesday to you, Wade. Wade, hopefully you're doing well. Elizabeth, good to see you. We got a lot of peeps in the chat. I'm very happy to see this. All right. Sorry, I missed class yesterday. I was at the doctor. They were worried. Ooh, oh goodness. As a man who has had appendicitis, yeah, that's not fun. I'm glad you did not have appendicitis. So, I have had an appendectomy. That is like not fun. So, my appendix is gone, long gone and removed. They took it out right before it was supposed to burst. So it's like, well, glad you guys got it out of there before I died. That's great. Like, you're the best, man. Oh, boy. Did they figure out what was wrong with you, Elizabeth? I don't know what's going on. Just waiting for results of blood tests. Very thankful. Yeah. Just be thankful it's not appendicitis. Man, post-surgery? Holy smokes. Oh, that's so brutal post-surgery. Ooh. Oof. Not sure you saw. Ooh, you're a member of hashtag now? Very good. Glad you could join the tag army, man. Welcome to the tag army, Aiken. All right. Welcome to the tag army. Did you buy some gear, by the way? I hope you bought some gear from the new hashtag store from Hummel. I think it'd be an ulcer, but I'm not sure yet. Ooh, yeah, ulcer's not fun. Ooh, let's hope it's not an ulcer, but if it is, hopefully it can be easily treatable. I'm telling you, those limited edition QR shirts, man, get on that if they have any more left. No, I bought some 3x 3x QR shirts, so basically I got those. Kind of fit me a little looser, I know, but Hummel's got a lot of class with those shirts. Those kits, man, is really good. Prefer to get the sponsored one, to be honest. Okay, very good. We got Lee Wen, we got Elizabeth. I know we're missing a couple of people here. Missing Emma and Nick. Let's see if they decide to make an appearance here, if they're not already here, that is. I'm not sure, but if they are, then hopefully they make themselves known. Can get going here with we got 2 sections here to do today, by the way. So we're still Emma's here. Very good. Hello, Emma. How you doing, Emma? Hopefully you're having a wonderful afternoon. Slash evening. Very good, very good. Aiken, my friend, get some gear. I'm gonna shill for hashtag get some gear. Man, get that gear. I'm telling you, I'm gonna shill for hashtag for a long time. Your park car came in and barely got in a 6-7. I barely got in a 6-7. I'm not sure what a 6-7 means in your grading structure, so you'll have to avail me of the information there. I'm not sure what that means. 6 out of 7. Okay. Is it? Yeah. Is that the grading system you have there, or is it just like? Or is that like a placement test of? Okay. IB. What's that stand for? Sorry, I'm so used to just the American Standard, or just American Standard's already rough enough as it is. So is it like a 7-point system where it's like 7 is like a high A and 6 is like a low A or something like that? Is that how it kind of works? It's like GCSEs but harder a bit. Okay. Yeah, every country's got like a different grading system. So okay, yeah. So then 7's like an A plus and 6 is like an A. 5's like an A minus. 4 is like a B plus. IB is pretty popular. I believe it. Yeah, I believe you. It's kind of weird over here because some systems only use ABCDF, and some systems will use actually the pluses and minuses. So depending on if you have GPA or not. Also, it also depends on. Actually, also may not be aware. Actually, it also depends on major as well. Some majors will use the plus minus system. Some majors will not use the plus minus system. So. Usually the majors that use the plus minus system are much more stringent. So it's kind of weird, but it works. All right. Hopefully Nick comes by. Surely not using the plus minus. Yeah. So for example, I'll give you an example. Like if you're in nursing, they have to use the plus minus system because of how competitive that major is and how strict that they have for certifying you to be a nurse since you're in the medical field. So they use the plus minus system actually, and most other majors use the regular ABCDF system, but nursing I know for a fact does use the plus minus system to weed out the people who are not who may not be suited for the field, so or they get cut from the program. So very strict about that. All right, ladies and gentlemen. Oh man, we gotta get started here. We gotta get going. All right, let's do this. All right, let's do this, ladies and gentlemen. Today, you're gonna like what we're gonna be doing here today. I promise you that. You're gonna like it. Yes. All right, let's do some intros and let's get moving. All right. Okay, let's get started today. Okay, let's get started today. Welcome back. I gotta do that again. Okay, let's get started today. Welcome back. I'm gonna die. Welcome back. Welcome back to Wednesday. All right. So today we're gonna be doing hopefully the last two questions. I'm gonna die here. Let me tell you. I don't know what happened to my breath. It was just like. It was a good effort. I know. Should I start from the top again, or should I start again, or maybe get that 5 liter water. I only got the coffee here. That's my leftover coffee from the morning. So, because my container of water is done. Okay, let's do this again. Okay, let's get started today. Welcome back to Wednesday. All right, third time's a charm. Welcome back to Wednesday. All right, so today, like I said here, we're going to be doing a couple of sections. I'll be posting up the final here today, later on tonight. That is the goal. All right, so that is going to be done and dusted here by the end of the day today. Remember that after tomorrow, you will have 2 more weeks, okay? 2 more weeks of which to finish everything, okay? 2 more weeks of which to finish everything. All right, so we are going to be going over some nice stuff here, at least to start with, and then we'll be going over some slightly tougher stuff, and then we're going back to nice stuff. So that's what we're doing. All right, so let's go to the big board here and take a look at what we're going to see. All right. Go finish your game of Valorant. Have fun, Aiken. Have a good night. All right. All right, so let's go to the big board here for today. And so for today, in section 8.2, we are going to be talking about partial derivatives, okay? We're going to be talking about partial derivatives. So question 1, which is the entirety of section 8.2, how do we find these partial derivatives? You know, first of all, we talk about the notation. The notation, as you can see here, is fx, okay? You'll see this little subscript of x, and what this f with the subscript of x represents is that is representative of the partial derivative with respect to x. We have fy, which is the partial derivative with respect to y, again with the subscript of y. We can also take second derivatives, so like fxx or fyy, fxy, fyx. These are, again, second derivatives. Again, order will matter actually doing second derivatives as well. So in the next section, the second derivatives will play even a bigger role about what we want to do for calculations. But for this section here, we're just going over basics, okay? Now, what's the easiest way to basically do this section, and why? You know, it looks intimidating at first with these partial derivatives. You have 2 variables, and like, I gotta do some derivatives with that? Like, that's crazy. But there is a big trick behind this that makes this significantly 99% easier. So the trick I put down is this, and this is how I think about partial derivatives every single time I do it. All right? The trick is to imagine that the variable you are not taking the derivative of is just a constant. That is the trick you are going to use when taking these partial derivatives. So it's like imagining, oh, it's just a constant number. So how much does it actually play a factor into the derivative? The answer is not much. Want to just look at the specific letter that we're taking the derivative of, and everything else is just extra fluff. So how do we go ahead and do some sample problems? Well, let's take a look at some examples here from our homework, and let's see how it works out. I think this is the one. Yeah. Okay. So we're just going to go over some basics here, and we'll just see how it works. All right. So I want to go over question 1, because, again, question 1 here looks, you know, you'll see the answers here for question 1. Actually, I'll take a wait here. Together. All right. All right. Meanwhile, while it does that. All right. So you've seen this. You've seen the answers here, but let's talk about this here. All right. So we have f of xy. Again, 2 variables. We discussed this here yesterday. we have 2x plus 6y is plus 4. Now let's take a look here at each of these, and you'll see why this is so easy when we use the trick. If we want to find the partial derivative with respect to x, so the way you want to approach this is, to do the partial derivative with respect to x, imagine, if you will, that this y here is just a constant. So all you have here is you have 2x plus 6 times some constant plus 4. Well, 6 times some constant is just a constant, and the derivative of a constant is 0. It would drop out. So all you're really doing is taking the derivative of 2x, and the derivative of 2x is just plain 2. That's it. Because we just use this trick, and we use and abuse this trick a lot. Pretty much every single partial derivative. So if we look at f of y, okay, fy here is the partial derivative here with is the partial derivative with respect to y. So again, we would imagine that 2x, again, we would imagine that x now is the constant. So 2x is just some random constant number, the derivative of which is 0. We take the derivative of 6y, which is 6, because that's fine. We could take the derivative of that letter, and 4 just drops out again. So then there you go. You end up with 6. All right? Hopefully that's not too bad. All right? So that's how you can get 2 and 6 here, respectively, for that. Easy peasy. Let's take a look at number 2. Why don't you guys help me for this one? You get hopefully into the swing of things here. So here we get 1 plus x to the third plus y to the fourth. Okay. Why don't you guys tell me, what is the partial derivative with respect to x? What's that going to be? What is fx going to be equal to? Hey, I'm glad you showed up, Nick. Good to see you, my friend. What is fx going to be here? Good afternoon to you, Nick. You came just in time. What is the partial derivative here with respect to x? Again, you're just going to imagine that y is a constant value, okay? Again, whatever you're not taking the derivative of, just imagine that it was a constant value. And that's correct, Emma. That's right. If y is a constant value, the derivative of any constant is 0. So we get 3x squared straight up. Sounds perfect. Emma Lee Wen, absolutely correct. All right. Now let's use fy. What's going to be the derivative here, the partial derivative with respect to y? What's that going to be? Or y to the third. All right. Seems rather reasonable. All right. Pretty simple. All right. So far, so good. All right. So we have 3x squared for the partial derivative with respect to x. And we got 4y squared partial derivative with respect to y. All right. Fine. And these problems here, pretty straightforward in terms of their approach. Requires very little effort at the end of the day. Okay. Now, let's take a good look here at a couple of others, though, that may require a little bit of work. But, in all honesty, not really. Okay, let's go to number 3. And I'm going to showcase this one off here. So number 3 has a function here. Looks a little intimidating. To be fair, it looks a little bit intimidating. But again, the word is looks, and not exactly it is. We have 9y over x to the 5th. Now what is helpful for you probably in this case is to probably go ahead and rewrite this problem out. So you can easily rewrite this as 9y x to the minus 5. Okay, so you have, you can certainly write it like that, or x to the minus 5 times y. Either case, you'll have that. Bother me all day. All right, damn science. All right, So, all right. So let's do fx here. Let's do the partial derivative with respect to x. Okay. So although you have x and y put together, okay, again, you're just going to imagine that y is a constant. All right, so one thing I want you to do here in this particular example is we're not doing the product rule. We're not doing anything like that here. Just going to imagine that y is a constant. So instead of 9y, for example, imagine 9 times y was like 90 or something, you know, some random number. I don't care what that is, but imagine it was just some random number. So you have some random number times x to the minus 5. All right. So what do you think that the partial? What do you think that? The partial derivative with respect to x is going to be here? What do you think that's going to be? What do you guys think? Give me a little hint about how you want to kind of approach this in your mind. So I'll write it like this, like 9y, that'll be like the constant. You have x to the minus 5, which is the real letter you want to look at. Negative 5x to the minus 6. Now, I would agree. So we keep the 9y the same, though, don't we? Right? It's just a constant number, right? And we multiply that by negative 5x to the minus 6. I'm going to add a little bit to this guy here. So if you multiply this, we actually end up with negative 45 y x to the minus 6. That's going to be the partial derivative with respect to x. So notice I just took the derivative here of x to the minus 5. This 9y was a constant. And there you go. That's all you need to do. That one. Before we move forward with the next, with the second half of this question here, are there any questions about that part in particular? Want to be extra sure that that's clear about how I came up with that. Okay. So again, if that's a little confusing, again, you can always go back to your rule of like 10x to the third. And you remember you just leave the 10 alone, and you actually just end up doing. So I always think about it kind of this way. Works the same way. All right. In any case, let's do let's do the partial derivative with respect to y. So this time here, x is going to be our constant. And we're just taking the derivative with y. So what's the derivative here in this case? What do you guys think? What's this partial derivative here? 9x to the minus 5. That, Liwen, is absolutely correct. Yes. That is correct. Using this little trick here, absolutely 100% correct. Yes. Very nicely done. Again, using our trick here of just saying, hey, this thing has to be... There we go. Yeah, so basically, again, if you need to see this more on the visual side here, again, 9x to the minus 5 is going to be like your constant, and then you have a y here. And so the y would just drop out, because it's like the same thing as like if I had 3x, or 3y. The derivative of 3y is 3. The y just drops out. Oh, okay. That's it. Right? Same deal. Alright, fine. Good. Sounds pretty decent to me. Alright. Any Any questions about that so far? Question mark. All right, let's do some slightly tougher ones here. 4 can be a slightly more difficult one here. I honestly think 5 is pretty easy, so I'll probably skip that one. But let's go ahead and take a look here at number 4. Number 4 probably is can be a bit tricky, so let's just go ahead and take a look at that one here. We have g of u comma v is equal to u minus v, and here we have u plus v bottom. All right, fine. All right, and here we're just going to go ahead and take the partial derivative here with respect to u and respect to v. So if I took the partial derivative here with respect to u, essentially, again, we treat v as a constant number. Now, because even if we treat v as a constant number, all right, in this case here, we're kind of forced to use in this instance, because of the way it's written, we are kind of forced to go ahead and use the quotient rule. Right? So the quotient rule here definitely is something that we have to use in this instance. So again, you can mark this as your f, your mini f, and your mini g. Be like your f, and this would be like your g. So here we have our f here with respect to u only. So again, you can imagine it as like u minus 1, for example, and this would be like u plus 1 if you really want to kind of... You can put any number in there. It's just, again, for visualization's sake. So basically that's going to be 1, and this g prime is 1. So then we have f prime g minus g prime f, f prime g minus g prime f over g squared. Okay, let's do this out here. So we have 1 times g, which is u plus v, minus 1 times u minus v, all over u plus v squared. All right, fine. That's perfectly cool. Okay, and then we just want to simplify the numerator here, so let's do that. By that. Here we get u plus v minus u plus v. Okay, now the reason why we got this is because we take this minus sign and we distribute it to both of these guys, so that's why we get the minus u plus v here. All right, and so we have a u, these u's cancel out. This leaves us with 2v over u plus v squared. All right, that sounds fine. Good, good. All right. So that's pretty much all you're really doing for that. There's really not a whole lot going on. It's the same stuff, different day, right? Let me zoom this out here. That way. All right. That's all you're essentially doing. That's it. You want it there to be more. There's not a whole lot more. So, yeah. Any questions about that? Oh, I put 4 by. That's correct. Okay. All right. Easy peasy lemon squeezy. All right. let's have you guys pick the next one here. That one's easy. That one requires like all right. Okay. Let's go over all right, so let me see. 6 and 7 are rather simple. They don't require a whole ton of effort, but I could show off one of them here. Which one do you want me to show off here? I will be doing like something like 8 and 9 and 10 and stuff like that. So, which one would you like me to do? Would you like me to do 6 or 7? You guys pick them. I just do them. Haha. All right, so it looks like we have a winner. Unless actually Nick has a vote, of course. I got here late, but he still has a vote. You want to do 6 or do you want to do 7, Nick? 7? Okay, let's do it. All right, so number 7 here. All right, so number 7 here is f of xy. Again, e to the x plus e to the y to the 8th power. Alrighty. So if we do the partial derivative with respect to x, again, y would be a constant here. So again, y doesn't have any bearing in the problem outside of just being a constant. So again, e is a special number, right? But again, if we take e to some constant number, that's still going to be a constant number. Again, you can imagine if you had like e to the x plus 1 to the 8th, if you want to kind of write it out or visualize it out. That 1 could be just as equivalent as e to the y, whatever. Okay, I'm just, again, making this stuff up. But again, it's pretty much the same representation, quote unquote. So the way I would want to do this is, basically, I'm just going to use the chain rule here. All I got to do is take the 8 on the outside here, keep the inside exactly the same, just as I would before. So e to the x plus e to the y. Take that to the 7th. And then I take the derivative of the inside here. Now the derivative of e to the x is still the same. It's still the same as e to the x. So I'm going to multiply that by e to the x. And that's it. That's the partial derivative here with respect to x. It is going to be 8 e to the x. Caret here. And we have e to the... How do you solve sine of x? Are you talking the derivative there? If you're talking the derivative, then you just use the product rule on that. Yeah, so the derivative here, okay, it's not so hard. You have sine x times e to the x. Again, you know that the product rule is f prime g plus g prime f. All right, so then all you gotta do is do the derivative of cosine. Integral, you can try it by... Integral may be a bit tougher. Off the top of my head, I don't remember. But I believe you might have to do that by parts. Or, actually, you may have to do that by... You might have to do that by parts. I mean, the integral of sine is going to be negative cosine. So... You could technically do that by parts, actually. So... They have a integral of sine e to the x, right? You can set u here is equal to sine. Du is cosine. Dv would be e to the x dx. And then that you would have v here be e to the x because that's the integral. Integral's super simple. So you have uv, you'd have sine of x e to the x minus the integral of v du. So let's see. Now you'd run into that issue again, wouldn't you? But if you, what would happen if you flip them around? Oh, e du. And you'd have to do that again. That would be might be more involved than I think it is. By parts, you would have to do that cosine. Cosine, that doesn't really go together. So yeah, e to the x, du would be e to the x. But you still have something in terms of x, and that's kind of what you're trying to avoid. Yeah, that's a little tough actually. I don't think I've done that in a while, unless that requires like a special rule. I'm probably missing, though. I probably am missing a special rule that goes with that. Probably it's like probably a special integration. Fortunately, in this class, we don't have to do that. But hey, you know, it's a question nonetheless. So, let's find out, shall we? See if I have to use a special rule for that or not. I don't think so. So I still have, what do I have? The integral of sine e to the x, right? Equals uv, that's sine e to the x, minus the integral of cosine e to the x. You have to do it a few times? Oh, okay, so you do have to do it a few times. Are you playing like a substitution game? Is that what you're doing? Because then that would make sense if you're playing substitution games. Actually, what happens if I do go in reverse? That's a good question. Actually, hold up. Hold up. Alright, now I'm kind of intrigued. Alright. What happens if we go in reverse? I know I'm getting sidetracked here, folks. I apologize. Once you start on something, you gotta see it through. What if I went in reverse? What if I did this? What if I did u as e to the x? And I have du as e to the x. And I had dv as sine x. That means I know that v here has to be negative cosine. So I get negative e to the x cosine minus the integral of... oh, that actually turns out to be pretty darn good. Actually, this actually turns out to be really good. Oh, this is good. Oh, I like this. Now this is worthy. Alright. Yeah. You don't have to do it like super twice, yeah. And then this is the integral of sine x e to the x. And so all you gotta do is add that to both sides and divide by 2, right? And then you add by c. Yeah, okay. Alright. I see what you're doing there. Alright, yeah. Gotcha. Okay. That's right. I haven't done that problem in so long. Oh my gosh. One of your favorite integrals to teach students? That's a good one. No, that's a good problem. Now in this class here, this is business calc, so there's no trigonometry. No trigonometry there. Could I clarify? Yeah, no crazy. Well said. I ain't gonna lie. You're not wrong. Or not wrong at all. I'm gonna have to erase this because I need to do number 7 here. Can I clarify? What answer could be given for GV and what answer would be given for GV? So GV here, again, if you need to, because it's partial derivative, again, just imagine u as a constant number. So again, you have one. I would like a brush. Not. Imagine if you had 1 minus v and you had 1 plus v, right? If you were to imagine it that way, Emma, then just do the quotient rule on that, where you have like this is your top function here, call it this your mini f and your mini g, and then just use the same rule again. Again, you're going to get mini f here is going to be -1, and mini g here is going to be the derivative of that is just going to be 1. And then apply the same rule again and simplify. So that's essentially what you're going to be getting for that one there. I'll have you try that though. I'll have you try that. It's not very hard, believe me. It's just one extra step by using the quotient rule there. It takes very little effort. That's how you can clarify that. Again, that's the trick behind all these partial derivatives. Just imagine that the other variable is constant, and then just work from there. It makes it like 50 times easier. You don't have to worry about partial derivatives after that. Like zero effort plays. Okay, I promise you, 0 effort plays. Oh yeah, I have to write in the answer here. I forgot to write. E to the x plus each y. Thank you for the love, by the way. I appreciate you. To the 7th, and there we go. Do the answer for f of x. All right, for fy, again, just to show this one off, again, you're going to do the same thing here once again. The only difference is that x is now the constant as opposed to y. So, here, made you mad. Made you mad, my buddy. I interrupt your regular programming to bring you a sub. Made you mad. I had a feeling you were going to come by today. I had a feeling. How you doing, my buddy? I hope you're outstanding. I was telling one of my friends that you were like, I had a feeling that made you mad to come by today. He was complaining about Founder's Badge. I'm like, oh, okay. I wasn't wrong. So you can imagine x is your constant here. You have e to the x. You've been busy? Well, it's good that you've been busy, at least. Busy in a good way, though. Hopefully been productive. You know, I hope so anyway, Major Man. With classes, there you go. Working our way up. Now, since you're taking the derivative of e to the y, because e to the x is a constant, again, you can imagine it as if you have e to the y plus 1 to the 8th power. Essentially, then you just multiply this by e to the y, and then that's all you're going to get here for fy. There's only one difference here in this particular one. That is, you have e to the y as opposed to e to the x. That's all you're going to get there. How many classes you got, Major Man? I believe you told me you had 2, right? If I'm wrong about that, just correct me. Alright. That's all you got to do for that one. Easy peasy. Yeah, it's 2 and the 4 in the fall. Very good. Easy time, easy life. Alright, and that would be the correct answer. Alright. Good stuff. Alright. Questions so far? Hopefully that's not too bad. Datus, thank you very much for the follow. It's really kind of you, my friend. Super kind. Thank you so much for the follow, my dude. You guys are super just like you and Major Mad and everybody here in the class. You guys make this super fun. Thanks, guys. I appreciate it. I really do. All right. Okay. Next, let's do number 8 together. All right. Hopefully that 8's not too big. Bet my eyesight is terrible. Alright, so let's do number 8 here together. This time we have 3 variables. We have x, y, z. And here we're given x, y, z plus x, y to the 5th. Okay, and plus y, z to the 5th plus z, x to the 5th. Alright, I'll move that up there. You guys probably can't. Alright. Okay, here we go. So, all we're going to do here is let's take these partial derivatives, okay, ladies and gentlemen? It will be pretty simple. So here we have fx. Alright, so let's go ahead and find out what the partial derivative here with respect to x is. Again, even if you have 3 variables as opposed to 2, the variables you're not taking the derivative with respect to, such as in this case y and z, just imagine that once again, both of those variables are constant numbers. Okay, so again, if you're not taking the variable with respect to that particular guy, well then, just imagine it's a constant at the end of the day. That's all you're going to be doing. So, take a look here at the very first part. Here you have x, y, z. Okay, that's what you got. So, well, we'll get to the rest of it in just a second. But what is the partial derivative with respect to x for just that first term of x, y, z? What do you think that would be? That's the real key question here. We'll do the others after that, but just want that right mindset here, even with 3 variables. We're not changing our approach here whatsoever. What would be that partial derivative of x, y, z? What do you think? Guys, take a stab, take a guess. It's fine. One YZ. Ooh. Okay, so it'd be just y times z, right? That's what you would say, Liwet? Again, you're just going to imagine that y and z are both constant numbers. That's what you're going to do. That's all you're going to do, really. Okay. And in that regard, Liwen, that would be correct. Yes, that is the correct answer. If you're just doing the first term there, the answer is yz. Again, if you wanted to group yz together as your constant number, multiply that by x. Again, the x would drop out because you're just taking the derivative of x. And then you just keep the yz. Again, it's like the same thing as like saying 3x. Derivative of 3x is 3, right? So you're just keeping the 3. The x drops out when you take that derivative. All right. That's it. How about that next term there? What's the partial derivative with respect to x for xy to the 5th? Let's do the rest of them. Xy to the 5th. What's that partial derivative for fx? What's that going to be? Y to the 5th. That's right. Very good, Elizabeth. Spot on. All right. How about yz to the 5th? What's that derivative? Partial derivative with respect to x for yz to the 5th. What's that? Just yz to the 5th? All right, ladies and gentlemen. What's y and z? Y and z are constant numbers, right? Because we're taking the derivative with respect to x. What's the derivative of a constant? We're assuming that y and z are constant numbers. So what's the derivative of a constant? Let's not forget. What's the derivative of a constant, everybody? This is rule number 1 here. Enter in your answer in the chat there. I'll wait for you guys. Oh, okay, good. The answer is 0. That is correct. Yes. So here, that's straight up 0. The derivative of yz to the 5th, because we're assuming that y and z are both constant numbers. Okay? How about that last one there? Zx to the 5th. Zx to the 5th. What do you think that is? Oh my gosh. 5zx to the 4th. That is correct. Very good. Good. That's correct. All right. So that's your answer for the first one. All right. Yes, absolutely spot on. So we get yz plus y to the 5th, okay, plus 5zx to the 4th. All right, fine. Okay, now it's time for you to put this together. Tell me what tell me the partial derivative here with respect to y is going to be. All right, time for you guys to put this together now. Now, I want you to be able to use this appropriately. All right. I'll give you a minute here. If you got an answer, put it down. But I'll give you a minute. I want you to tell me what this is going to be. That's the first term there, Emma. Give me the whole thing. I agree. That's the first term there, though. Give me the whole derivative. This whole partial derivative here with respect to y. But yes, that is the first guy. I agree with that, xz. Again, once you got your answer there, go ahead and type it out in chat. Okay, let's see here. Okay, not quite, Elizabeth. You have the first two are correct, but not the last two. Again, use the trick that we have here. Go back and use our trick. What does the trick say? Imagine that the variable you are not taking the derivative of is just a constant. Lee Wen says xz plus 5xy to the 4th plus z to the 5th plus 0. Okay. That is correct. Very good, yeah. Had to look at that one again. All right, so 5xy to the 4th plus z to the 5th. And we have zx to the 5th, but because that's a constant, because that's both z and x are going to be. Again, the derivative of a constant is 0. So it effectively drops out. Okay, that's fine. Not a problem. What about f? Are there actually, before I go on to FC here, are there any questions? Any questions at all? I want to be sure that there seems to be a point of confusion, so I just want to be sure that I address that before I move forward. If there's a point of confusion, let's at least talk about it. What's any questions at all, guys? All right. So if there are no questions, I'll move forward. Okay, so let's do FZ here. All right, so FZ here, again, we can do this pretty quick here. So we get XY. Again, we get XY here because Z is going to be our variable and XY are constants. There are no Z's here for that second term, so that's going to be straight up 0. All right, that's correct. And we get 5yz to the fourth. Okay, so we get 5yz to the fourth for that third term. And we get plus x to the fifth. That is correct. Okay, very good. Nice job, Elizabeth and Lee Wen. That is correct. Very nice. Nicely done. Okay. Again, you don't have to add the 0, obviously. That's just a way to kind of showcase that drops out. So you would just write in your answer without the 0, but you get the general idea. All right. Good, 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 good. All right. Progress has been made. All right. As for evaluating the partial first derivatives, they're pretty simple. Again, you just plug in the numbers after finding the first derivative. So you're not doing a whole much here. If you were to do it like in this example, let's say I did f of z of, let's say, 1, 2, 3. You just plug in 1 in for x, y 2, and z 3. So literally, you find that first derivative, and you just plug in numbers. That's all you gotta pretty much do. So that's all you pretty much have to do. So you get 2 here. 3 fourth is 81. You get 10 times 81. 10, get 81. 1. What is that? 2 plus 8, 10. So we get 813. All right, fine. All right, so evaluating is very easy. I'm gonna kind of skip over that because it's just pretty much straight up, hey, just do it. All right. Now, I'm gonna show one of these examples here. Yeah, just one of these. And then the others are gonna be kind of for you to do on your own. Okay. So the next one I want to do is second derivatives here. So let's go ahead and do second derivatives here. We're just going to showcase one of them here. I will do... They're all pretty similar. So I'll just do number 12. Number 12 is pretty okay. So these, let's say again we have this function in 2 variables. We have x squared minus 5xy plus 4y squared plus x minus 6y. Okay, so here we get fxx. Okay, so let's say this is what we have here. Okay, Now to do the second derivative here, if you see notation like this, again what we're going to do is we're going to find the partial derivative with respect to x, and then find the partial derivative with respect to x again on that subsequent result. So basically what you're doing is this. You first find fx, okay? Find the partial derivative with respect to x. Now if you do that out, you'll get 2x minus 5y plus 1. So if you do that out, this is what you're going to get. I mean this in the most polite and shitty way. That's fair. Where is this real-life situation be used? Well, there's application problems regarding productivity. So if you're talking about putting metrics on productivity, you can actually use it. So productivity is where this is mostly used, at least in business. So like, you know how they come up with a metric of how productive of a worker are you? Well, you can make a metric out of that using partial derivatives as a way to kind of justify that. Like those guys behind the scenes, like, yeah, it means a lot. So, I mean, there is a real life application to it. You know, there's a lot of there's different applications, so certainly, but productivity is a pretty popular one. Even the chapter goes into talking about a particular type of productivity stuff, which we're not going to get into in for the purposes of this course. We're not going to really get into that, but yeah, there's actual practical applications there. Them metrics, let me tell you, them metrics, they mean a lot. You ever wonder how they come up with benchmarks? It's fairly interesting. Math is one of those things that, you know, it's subtle. It's, you know, some things are easy to see, some things are not so easy to see. You know, but it can be subtle, it can be very direct, but it is, again, useful in some shape or form in certain aspects. The question really comes down to this, Elizabeth. Are you going to necessarily use it for what you are going to do? The answer will be probably not. But again, is it useful at least in some capacity somewhere else? The answer is yeah, most definitely. Like a good example is like, oh, people ask, where would I use parabolas in real life? I'm like, just look at the road. That's all you need to. It's what you need to see, right? I'm a business minor to open my own vet clinic one day. Oh, I hope you do. Will this be useful in terms of productivity? Maybe. Maybe. I don't think you're so much of a corporate culture, though. I mean, you're trying to, of course, the one thing you'll have to be careful about, of course, like any other medical facility, is, of course, make sure that costs are, you know, the costs that you take on, you know, don't negatively affect the clinic in any way. The toughest portion of anything that you do in a business is always the first 2 years of the business. So you have to play it really safe the first 2 years of the business. And once you get to a break-even point, that's when things start ramping up quite a bit. But it's usually the first 2 years because those are the first years are the ones where you're actually taking on so much debt, you know. Like, you just can't, like, open up a vet clinic and be like, oh, I got a vet clinic. And it's like, well, what do you got in your vet clinic? And then you're like, I got a table. I got a chair that you can wait on. Yeah. Like, maybe you need some equipment. Maybe you need some staff. You know, maybe you need to balance that out. Like that revenue cost stuff with fixed costs, like especially the fixed cost. You're going to have to take out a loan for, you know, no matter what, Elizabeth, if you're going to open up your vet clinic someday, you're going to have to take a loan for, like, you know, location, first of all. You know, how much is it going to cost you to rent the space or at least build on the space, depending on where you open up the vet clinic. You know, how much is it going to cost you to actually get all the equipment? You know, that could be ranging in the hundreds of thousands of dollars because some of that equipment isn't cheap. Okay, certainly like x-ray machines, they, you know, they're not a... You could get x-ray machines, but they're not not cheap at all. And you have to get like the materials for it as well. You have to get the staff. You start off small, but still, and you got to make sure that your material costs and things like that for treating pets and whatnot isn't going to outweigh. You want to make sure that it doesn't take up a too big of a burden of your business. So again, that's why vets are pretty expensive, because those things cost quite a bit. It's not easy to maintain. Those are pretty high costs. And until, like I said, when you reach your break-even point, then that's something else. And often vet clinics also double as volunteer centers for, say, for example, like spade or neutering. Okay, what's that called? TNR. You probably have heard of TNR before, Elizabeth. So that could be, again, something more practical, at least in that regard. So that costs money if you're doing TNR in and around your area. TNR, for those of you not aware of, is trap, neuter, and release. So that's essentially like stray pets in and around like areas. They often try and trap animals, so they neuter them. They control the population in those particular, say, urban centers or whatnot, so that way it doesn't get out of control. Helping that equal out the costs of what I actually do at the clinic, because I want to be a vet surgeon that specializes in cancer and tumor removal. Would be nice. Nice area where people would be willing to pay for the pets. Yeah, that's still going to cost you a pretty penny. If you're going to be in a nice area, it's still going to cost you a pretty penny. But don't forget, if you want to be I understand you want to specialize in something, but a vet is seen as kind of like an all-encompassing thing, right? You could specialize in one thing, but you want to be all-encompassing. So that way you can get as many people to come to your clinic as much as possible. So just be sure that you got a wide variety of things that you can do at the vet clinic, so people can rely on you to come and say, hey, I need you to take a look at my cat. What's wrong with them? It's not just like tumors. Oh, your cat's got blah 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 this. So build up that rapport. Let me tell you, community rapport, number one when it comes to vet clinic. Community rapport. Being all-arounder is actually really good. And then you could take your specialty, take that to the next level. There you go. Right. Let me do this. All right, let me do, okay, we take the derivative here. We do fxx. Now, if you do fxx here, that's very, very good. I agree with that. Get to learn other languages. 100% behind you on that. You can be a polyglot eventually, so you're fine with that. So here we just take the derivative of this resulting function with respect to x, again the partial derivative, and so that way, in this case, that'll be just 2. That's all you're going to get here for that one, is you're just going to get straight up 2, for example. So that's what it comes out to be. Let's try fxy. Alright, so fxy just relies on this same function here. Again, now we take this derivative with respect to y, the partial derivative, and again the partial derivative with respect to y, after we take the partial derivative with respect to x, is just minus 5. Simple enough. Again, one of the things that is important here, again, just remember, order matters. Order matters a lot when you're taking the second derivative here. Be sure you're doing that correctly. Alright, next is fy, say fyy? Check that. Fyy or fyx? Fyx, okay. Alright, so for fyx here, we need to find the partial derivative with respect to y first. Let's find out what that is, and then we can find out what fyx is. The partial derivative with respect to y here, according to what we have, is minus 5x plus 8y minus 6. Alright, so that's the partial derivative with respect to y. Again, just assuming that all x's are constant. And we have fyx. Again, just take the derivative with respect to x of this function here of fy. That's going to be just minus 5. And then finally we have fyy. Take the partial derivative with respect to y. That's going to be 8. Okay, and that's all we have to do for that, at least in this case. Obviously, you can see where this is going. You know, find that first partial derivative, and then take the next partial derivative with respect to that next letter over. And then there you go. You got it. It's pretty straightforward after that. Okay, any questions about that? Any questions? Emma said no before. Emma's like, I'm sick of this stuff. I'm out. Emma's like, no, I don't want to listen to your voice. Like, oh, yuck. I think this is what Emma's thinking right now. Now, Emma, you can correct me if I'm wrong. Like, Emma's like thinking, man, this guy goes on so many tangents while he's doing a problem. It's like, I'm so sick and tired of this. Just get on with it already. Come on, dude. What's wrong with you, man? What's wrong with you? That's what she's kind of saying in her mind. You know, and I'm just kind of verbalizing it right now. Now, I'm thinking that's what she's thinking right now. Like, this guy needs to just shut the hell up. Just get on with it already. Like, dude. Man. It's just dropping complete bombs in her mind of like, oh, I totally get it. It's not what I'm thinking, don't worry. Okay, let's see. Emma's like thinking, get this over with. Yeah. Because I know for a fact Emma's like looking at me like, Emma's looking at the corner of the screen with me like, oh, who's that? You know, there's no way in heck Emma's thinking, who's that handsome dude in the top corner of my screen? Like, no. I wouldn't think that either if I were to view myself, okay? Because I know for a fact it ain't that. I'd be like, there's some numbers on the screen, there's some mathematics, and what's this dude? This dude that I paid money to. Who is this guy? Why are you here on my screen? Oh my gosh. All right. Let's go ahead and take a look at this last problem here, this word problem for section 8.2. I don't even know if I'm going to get through this. I doubt I'm even going to get to the next section here today. Oh my gosh, I'm having too much fun here today. Okay, alright. Oh my gosh, you guys make this so much fun. Alright, let's look at the productivity of a company. The number of souvenir coffee mugs in hundreds that Ace Novelty can produce monthly is given by the production function this. Okay, where X denotes the amount of labor utilized measured in thousands of work hours per month. and Y denotes the expenditure on capital investment in thousands of dollars per month. Okay, find the marginal productivities if 10,000 work hours per month are utilized and a capital investment of $5,000 per month is made, and interpret our results. Okay, now this problem here can be very tricky, but what I will point out here is you just need to read the word problem here a little bit carefully. So before we answer the stuff on the bottom here, this bottom paragraph, we'll get to that in just a second. But I want you to understand what this means in terms of the context of this problem. It says here, X denotes the amount of labor measured in thousands of work hours per month. So when it says thousands of work hours per month, it says, okay, we have 10,000 work hours per month of labor. So essentially, X is not going to equal 10,000. X is just going to straight up equal 10. Again, 10 here will just represent 10,000 since everything is in terms of thousands. Y here is not going to be equal to 5,000. We want it that's also in terms of thousands. Y here is just going to equal to 5, again, representative of 5,000. This is really important here as part of the problem in order to solve for the following two guys that we have here. So want to actually understand that this is going to be 10,000, 5,000 here. Now, why is this important? Well, the reason why this is important is because if we're going to get the latter half of this answer here, what we're going to need is we need to use 10 and 5 here respectively for both X and Y. So it says, let's read that last paragraph here really quick. It says, with labor at 10,000 work hours per month and a capital investment of 5,000 per month, an increase of 1,000 work hours per month with capital investment held fixed results in a production increase of blank mugs per month. So basically, don't let the extra 1,000 fool you. You're not doing anything really different here in this problem. What do I mean by that? In this problem here, you're taking productivity from two different points of view, i.e. the points of view here being you're going to take the partial derivative of productivity with respect to X, and you'll also take the partial productivity here with respect to Y. Here, basically, we had fixed capital investment. So basically, that means I take the partial derivative with respect to X, since we're not focusing on capital. The other side says an increase in 1,000 per capital. So it says, okay, fix the labor hours and increase the capital. So in that case, we don't care about the work hours. We throw those away and we say, okay, we're just increasing the capital. So we take the partial derivative with respect to Y. And we're just going to find out here the partial derivative with respect to X of 10 and 5, and the partial derivative with respect to Y of also 10 and 5. So we need to find out both functions according to what we're given here. Okay. So let's find out the partial derivative here with respect to X for this function. All right. So let's take a look here. We have 0.3x squared, so that's going to be 2 times 0.3 times x, so that's 0.6x. I have 5x, that's plus 5. Okay, so that's fine. 4xy, again, imagining that y is a constant. So we drop the x, essentially, and then it leaves us with 4y. 0.4y squared, that's constant, so that drops out, that's 0. And 2y, also constant, that's 0 as well. So those two not in there. Okay, now if we're going to evaluate this at 10 and 5, we're just going to plug in 10 and 5 into this result. We get 0.6 here times 10 plus 5 plus 4 times y, which is 5. So this equals 6 plus 5 plus 20, which equals 31. Now, also what's important here, by the way, I do want to point one thing out here, and what can be tricky in this problem, and what they want for your answer here, excuse me, is that notice that the number here, after you plug it into that function, is in terms of hundreds. Okay, so when we get the answer of 31 here, which is correct, all right, this is not just 31 as your final answer. This is reflective of 3,100 mugs, okay? So our real answer here is going to be 3100. Okay? That's what we're going to put down here, 3100. All right? All right. Now we just repeat this process here for the partial derivative with respect to y, and then plug in 10 and 5 into that function. Py here is equal to, let's see, 0.3x squared, that drops out. 5x, that drops out. 4xy, well, the y drops out, so that leaves us with 4x. 0.4y squared, we get 2 times 0.4. That's going to be 0.8y plus 2. Okay, and then we just plug in 10 and 5 here respectively into this partial derivative. So here we get 40, and here we get, what do we get, 4 and 2. So here we get 46, we get 4600. All right, so let's go ahead and submit this and see if we got it. Okay, and we'll scroll over here. And there you can see 3100 and 4600 here are the correct answers that we want. Okay. Questions about that? Any questions at all? Okay. All right. So, I was gonna try and get through 2 sections here today, but I guess we didn't. That's okay though. We can easily finish the last section tomorrow. I'm gonna need more than about half an hour to finish that one, so there's just a lot to do in that particular section, and 25 minutes isn't going to really cut it, to be perfectly honest. So we'll go ahead and forego doing the second section here today. We'll finish that off here tomorrow. It's not like it's not like a big deep section here, but again, it just does require a lot of some calculations. So we're gonna go over some examples here slowly in order to get that done. Remember that tomorrow, the last section, that is the last section, okay? Section 8.3 is the very last section in the textbook. So after that point there, starting next week, we're going to be doing review for everything, okay? So we'll be, you guys have questions that you would like me to answer for review, homework questions and the like, please let me know here. We're going to be starting that here next week, okay? So again, just because we don't have any new material doesn't mean that we're necessarily done. It just means that we just have that much time for review. So that is what is going to be on the docket here moving forward. As I've probably mentioned it before, but I'm just giving a friendly reminder. I'm going to be working on that final here today. That is the goal. All right. So that will take care of what we are going to be doing here for today. If there are no more questions, I want to thank everybody here for coming on to the stream here today. Thank you, Major Man and Aiken for the subs. Really appreciate it. You guys are absolutely outstanding. Thank you for the follows. Thank you for the nice integration problem with trigonometry. It was really, really cool. Thank you so much for today. Thank you so much for today, everybody. Thank you again, all of you, absolutely fantastic. Emma, Elizabeth, Lee Wen, Nick, thank you so much, you guys. You guys are amazing. I don't care if there are only 4 people that ever show up. You guys constantly show up. You guys are consistent, and I trust that you guys are going to be very successful in this course. So, thank you guys so very much for for spending a good chunk of time out of your day with me every day, Monday through Thursday. You guys are very kind. All right, we'll come back tomorrow, finish off section 8.3, and then yeah, next week will be yeah, start of review. So have those questions ready. We're gonna be taking on anything and everything for 2 straight weeks. So most definitely. All right. Okay, everybody. Yes, we'll see you tomorrow. All right. I'm ready for the timing. Let's do it. Okay. Thank you very much. Thank you very much, everybody. Take care of yourselves. We will see you tomorrow. Have a great one. And as always, everybody, stay safe, stay healthy, but most importantly, stay sane. All right? Have a great one, everybody. And we'll see you then. Stay sane. That's right. The COVID, man. Tell you, that's where I came up with that, because of COVID. All right, take care, everybody. We'll see you tomorrow. All right, have a great one, everybody. All right, bye. Bye, everybody.